moment of force. So there are two things over here. We are finding the turning effect basically, and we are considering the force applied and what is the distance from the point where it is fixed. As in, suppose there is this door, okay, and this is the hinge, the place where it is connected, and this is the free end. This is the free end. So when you apply force, this is the handle. When you apply force here, so we consider what is the amount of force and we check for this perpendicular distance. So if you have the product of these two, that gives you the moment of force. So basically, the definition, or how do we explain moment of force, is in terms of these two quantities, the force and the perpendicular distance, which is the product of these two, and that is how we get the moment of force. All right, so greater the moment of force,
Okay.
more will be the turning effect. Do you get that point? If moment of force is more, the door
Yeah.
is going to be rotating much easier and much faster. Imagine the position shifted. If the handle was somewhere very close here, then the value of moment of force would be reduced. It will become less, and then you will not be able to open or close the door effectively. So that is a basic concept of moment of force. This is how we find it. And as far as the unit is concerned, you substitute their individual units, Newton for force and meter. It will be very less, maybe in points, but whatever. So it will be meter. Another thing which you have to keep in mind is never replace this, never replace this by joule. Although, you know, work is force times distance, isn't it? You know that. There the force is again in Newton and the distance in meter. There we say the unit, SI unit of work is joule. But since moment of force is in no way, in no form, this is energy or work. It's not any of these. It's neither work, it's neither energy. So we cannot use joule.
Yeah.
Yeah.
And unlike, suppose I was talking about potential energy or I say kinetic energy, then what we say, since these are the forms of energy and work is a form of energy, then we can take this as the unit for both. All right, there we can take it, okay? That potential energy has joule, kinetic energy has joule, although their formula are different, but their originality is what? What is that basic thing which is similar in these? They are the forms of energy. Work is a form of energy. So basically they all are the forms of energy. So we can use joule for it. Okay, that is just an explanation to why we should not take joule for this one. It will only be written as Newton meter. Then comes the principle. What is the principle of moment? That what law governs the balancing of a lever or the balancing of any structure, you can say. The principle of moment states that the anti-clockwise moment should be equal to the clockwise moment. Now, anti-clockwise moment and clockwise moment, unless you know what they are, how can we equate them? So let us understand that. Consider this to be the lever. This is the fulcrum about which it moves. And let us have the two directions of forces, one directed down, one directed. Okay, let us take both directed downwards. Now, this is the fulcrum. So this is A, suppose, and this is B force. So you will extend and you will try to go towards the fulcrum like this. So you are pointing this way and see the direction of the movement, and it is anti-clockwise. So we are having the anti-clockwise movement for this particular force. Okay, let us see this one. Again, we move towards the fulcrum, always towards the fulcrum from the tip of the arrow. You will go like this, and this time you find that your arrow is pointing in this direction, which is clockwise. So this one is giving you anti-clockwise movement, and this is giving you the clockwise movement. And you can relate it very easily with the seesaw. In the seesaw, person sitting here and the person sitting there, both sitting at equal distances. Suppose both are weighing equal, then it is going to be horizontal. It is going to be in equilibrium. Neither it will go down nor it will go down this way, because both are of equal weights. And how do we find that value? Anti-clockwise moment, it is moment only, the product of this force, that means A force, and this distance. This distance is x, even this is x, because it is in the center. So here the moment is A times x, here the force is B, force times the distance, this is there. These two are equal, and also A is equal to B. We have assumed that both the forces are equal, so this is going to be equal. So it is obeying this principle of moment, hence we can write in equilibrium. So first thing is you need to check what are the values of clockwise and the anti-clockwise moment. Then you have to see whether they are equal. If they are equal, they will be in equilibrium, it will be horizontal. If they are not equal, it is not in equilibrium and it's not going to be horizontal. It will be tilting in one particular direction wherever the moment is more. Okay, and you have to be careful while seeing the directions of these arrows. If this arrow was up, then this was anti-clockwise, even that would have been anti-clockwise. That time it will give you a rotatory effect, a rotatory motion would be seen, but it will not be in equilibrium.